So now we're going to talk about that nuance that I mentioned at the end of the last video. So if we're looking at the arctangent approximating polynomial, let me bring that back up so you can see it. As I mentioned, this approximating polynomial does not actually converge to the arctangent function for all numbers. So, for instance, if I try and calculate the arctangent of the value 2, then there is a number, it's like 1 point something, maybe 1.1, who knows. There is a value, but this approximating polynomial is never going to be able to come up with it. Because even with the maximum number of terms that I can put with this function, or with this program, which is 20, the closest I get is pretty much a maximum of +1 and a minimum of -1. Now, the approximation is very good on that range, but to be able to calculate the arctangent of 2, we'd have to do something different. One thing we could do, as I mentioned, is you could recenter the polynomial. So if you recentered the polynomial at, say, +2, then you could potentially come up with those values. What that might look like is this. So let me take my arctangent function, and I'm going to recenter it. Actually, I'll recenter it at +1. And I need to change my slider max. I can't do a maximum of 20 here because the program has to compute derivatives for arctangent. And the derivative of arctangent is 1 over 1 plus x squared, which requires a quotient rule to get the second derivative. And the calculation balloons from there. So I'm going to do that. It's going to actually take a moment to even get 6 derivatives here. Okay, I had to turn off a lot of switches and options here to get this to work because the computer is really redlining here with video editing software running and computing all these derivatives and whatnot. But here we are. I've recentered the approximation at 1. So that just means that the first linear approximation agrees at only this one value, which is here. Okay, now if I increase and get a second term in this approximating polynomial, then it's now a better approximation. It's linear, okay? But we're getting better approximation. And as I increase the number of terms, I should start to be able to converge on the value 2. So as I increase, you can see here that the approximation at 2 is starting to work out. Since I centered at 1, it looks like it's going to converge between 0 and 2, and that's about it. Perhaps if I centered at 2, then I could reliably get that estimate, and then from there, get convergence around different values. But that's the idea, is that you can use different places to recenter your polynomial to get the approximations anywhere that you need to. So this sort of, makes us question, how do we know where these values are going to converge or not? Because if you can graph the polynomial and you can compare it against the real numbers, well, then certainly you can determine whether or not you've got the correct value. But if you don't know what the values are supposed to be in the first place, how do you know that you have a value that you've converged upon? That's where our series tests from before come into play. We can determine the convergence of a series using one of these tests that we determined. And here, the most useful test is actually the ratio test. The ratio test is a very clean result. You just have to compute an infinite limit, and It works for both alternating and non-alternating series, which is great because in terms of power series, we actually have a lot of alternating series. So the ratio test is great here. What we'll do is we'll compute the limit that is required in the ratio test, and we'll compare that to 1. So we'll make that comparison. The result of this comparison is known as R, and we call that the radius of convergence. And for whatever that radius of convergence is, then exactly one of the following will be true. If R is equal to 0, then that tells me that the series is only going to converge at that one specific value that I've centered upon. Okay? If R is equal to infinity, the series is going to converge for all real numbers. And there are plenty of examples of power series where this is true, where it converges for all real numbers. If R is some number between 0 and infinity, then that means that it's only going to converge for a specific range of values. And that range of values will be known as the interval of convergence. But of course, the interval of convergence could be just a single number. The interval of convergence could be all real numbers, or it could be the actual interval that we solve for here. It just depends on the result from our ratio test. So let's take a look at some series. We'll come back to the arctangent function at the end, but for right now, let's look at some different series and kind of get an idea of how we can determine the convergence of a power series. Okay, so the first series that we're going to find the convergence of is this one right here. So we have the series n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. If you'll notice, this is actually really close to the arctangent. It's just that instead of the denominator being only 2n plus 1, it's 2n plus 1 factorial. And let's see what happens here. So we do the ratio test. So in order to find the interval of convergence, we'll always start with the ratio test. So in this case, let's see what we get. So to do the ratio test, we do a limit as n goes to infinity of the n plus 1th term, and remember, we're taking the absolute value of everything, so the alternating term doesn't matter. So you can ignore it. So this would be x to the 2 times n plus 1 over 2 times n plus 1 factorial. All right, and then we divide that by the nth term, which effectively just means to multiply by the inverse of the nth term. Okay. Now, we work this limit until we can find a result. So let's see what happens. So this would be the limit as n goes to infinity of x to the 2n, and then the 2 will distribute, so this will actually be 2n plus 3, and this will also be 2n plus 3 factorial, all right, times 2n plus 1 factorial over, and what's nice is x to the 2n plus 1 can change into x to the 2n times x, which is something that I will also do in the x to the 2n plus 3, so x to the 2n times x cubed. And this factorial, you can always pull off the top items of a factorial and leave the remaining terms. So if I take 2n plus 3 off the top, that would leave me 2n plus 2 factorial. Then I'm going to take 2n plus 2 off the top of that, leaving me 2n plus 1 factorial. And I'm going to run out of space here, aren't I? But anyway, that's still multiplied by 2n plus 1 factorial there in the numerator over x to the 2n times x, which means x to the 2n and x to the 2n will cancel, 2n plus 1 factorial will cancel here and here. And now I have the limit as n goes to infinity of x cubed is all that's left in the numerator. And then I have x times 2n plus 3 times 2n plus 1. And here's something that's kind of interesting. So x is a variable, but it's not changing with respect to this limit. So it's really considered a constant within this limit. And any constants can be pulled out of the limit. And if you'll notice, if I take x cubed divided by x, that would leave me with x squared, which is also positive, and that means that I don't really even have to worry about the absolute value on the outside of this limit. You could put the absolute value around it. It really wouldn't make any difference, but now I'm just left with this. And actually, I made a mistake there. That was supposed to be 2n plus 2. You all probably caught that and have told me in the video. All right, so then let's see. This limit, I have a rational function. The denominator is increasing, but the numerator is not changing at all. The value of that limit is 0. So this whole thing results in 0. Now, be careful, because it looks like you have a radius of convergence of 0, but that's not the case. You don't have the radius of convergence until you compare that limit to 1. All right, so you actually perform the ratio test. So this statement, 0 is less than 1, that is true for all values of x. So what that means is my interval of convergence is negative infinity to positive infinity. Okay, let's take a look at another one. You'd be surprised at just how different some of these examples can be. Here I have n equals 1 to infinity of x to the n over n. Let's see what happens here. So for my ratio test, just to get me started here, I would have the limit as n goes to infinity of the n plus 1th term, so that's going to be x to the n plus 1 over n plus 1. And then I'm going to multiply that by the inverse of the nth term. Okay, so limit n goes to infinity. This would be x to the n times x over n plus 1 times n over x to the n. This time the x to the n's cancel. X is still a constant here. I could pull it out. I wouldn't need to put absolute value around it because it's not like x squared. That would always be positive anyway. But that's fine. And that leaves me n divided by n plus 1 inside this limit. And that's a rational function. The degrees are equal. The leading term coefficients divide to 1. So that means that this results in the absolute value of x. Okay? Now that doesn't tell me anything about the radius of convergence yet. What that tells me is that I need to compare this result to 1, and only when this is less than 1 will this converge. So this converges when the absolute value of x is less than 1. So what that ultimately means is the radius of convergence here is 1. This could also be interpreted as x has to be between -1 and +1 in order for it to converge. All right, so if x is between -1 and +1, this series will converge, but that doesn't tell me what happens at the endpoints. So unfortunately, one additional thing you have to do if your radius of convergence is not 0 or infinity is test the endpoints. All right, testing the endpoints generally goes pretty straightforward. We take each of the endpoints, so when x is -1 and then when x is +1. Plug that into the series. So that's going to be the series n equals 1 to infinity of -1 to the n over n, because you're just letting the x value be -1 in that case. And over here, the series from n equals 1 to infinity of 1 to the n, which is just 1, over n. We have to decide if these things converge or diverge. And usually at this point, there's not a lot of work involved. This is the alternating harmonic series. And we know that that converges. Right? We don't really need to go through all the tests there. We can safely assume the alternating harmonic series converges. This one is the harmonic series itself. And we know that that diverges. So it converges at -1, but it diverges at +1. So that means the interval of convergence we write this as an interval. It's going to be -1 inclusive up to +1 exclusive. And then that's all the places where this particular series would converge. Here's another example. This one is slightly different. It's been recentered. Okay, and we'll take a look at what happens here with this particular recentered series. So to determine interval of convergence, the first thing that you're going to do is start with the ratio test. So we want that limit as n goes to infinity. The alternating term doesn't matter, within the absolute value that is. And then we would have x plus 1 to the n plus 1th power over 2 to the n plus 1. All right, and then in the denominator, well, we would be dividing by the nth term, which is the same thing as multiplying by the inverse of the nth term. Okay, now the next step is generally doing a little bit of algebra to simplify things. Here I could express this as x plus 1 to the nth times x plus 1 over 2 to the n times 2, and this would be 2 to the n over x plus 1 to the n. So the x plus 1 to the n will cancel, 2 to the n will cancel, and there's no other terms with an n here, so this whole thing's just a constant. So this results in the absolute value of x plus 1 over 2. That's only going to converge when that is less than 1. So we need to solve this inequality here to figure out at least the starting point of where the interval of convergence is. So if I take x plus 1 over 2, absolute value less than 1. That's the same thing as splitting this up into -1 less than x plus 1 over 2 less than 1. That's just how you solve an absolute value equation like that. Next step, multiply both, all three statements by 2 to get that out of the denominator. So -2 less than x plus 1 less than +2. And then that effectively tells me my radius of convergence is actually 2, but the only thing that really matters is it's 0, infinity, or something in between. You don't actually have to solve for the radius of convergence generally. Next up, if I subtract 1 from all parts here, this would be -3 less than x less than 1. So my interval of convergence is basically going to be the interval from -3 to 1, but I do need to check to see if either of these endpoints converge or not. So, in testing my endpoints, I just let x be -3 and then x be +1, plug that into my series. So the series looks like this. I would have the sum n equals 1 to infinity. It's -1 to the n. And then x gets replaced with -3, so -3 plus 1 is going to be -2 to the n over 2 to the n. All right, and then when x is 1, I'm going to have this sum, n equals 1 to infinity, -1 to the n, and this would be 2 to the n over 2 to the n. And like I said, these things generally very quickly solve themselves. So for instance, here the 2 to the n's cancel, and I'm just left with the infinite sum from n equals 1 to infinity of -1 to the n, which is just -1 plus 1, minus 1 plus 1, minus 1 plus 1. It never converges to a value because it keeps flip-flopping. So this diverges. Oops. Really, it's by the divergence test. Because those sequence terms are not going to 0. Okay? In the other one, what I can do, whenever I raise a value to an exponent, well, actually, I can think of -2 as -1 times 2. And then I can take each of those values in the product raised to the same power. 2 to the n cancels 2 to the n. Then -1 is always in, or -1 to the n is always in step with -1 to the n. So this would always result in +1. So this is just the series of +1, and if you just keep adding a constant, it's going to diverge, and this is also by the divergence test. So like I said, it's pretty rare that you would actually need to do one of the more advanced tests when you need to test your endpoints, because you've already done a ratio test in the problem. So generally, you're given an example that you don't have to do much work when you test those endpoints. Okay, so that brings us to the last example here. And as I mentioned, I was going to go back to the example with arctangent. And that's what we have right here. So this is the arctangent example. It's starting at n equals 1 instead of 0, which is why I have -1s. It doesn't really make a whole lot of difference. But I think what I'll do is actually start that back at 0 and then make these positives here, just to be consistent with what we were doing earlier. So this is the arctangent one. Okay, so we start off with the ratio test. And that would involve a limit as n goes to infinity. The absolute value, alternating term, disappears from the absolute value. And then I have x to the 2 times n plus 1 over 2 to the n plus 1 plus 1. Then we multiply by the inverse of the nth term. And that's what we get. Then this equals the limit as n goes to infinity. The numerator here 2 times the quantity n plus 1 would be 2n plus 2, plus another one would be x to the 2n plus 3, which I'm going to go ahead and write as 2n, x to the 2n times x cubed, just to save a step. The denominator would be 2n plus 3, we can't split that up. Then I have 2n plus 1 here, and I'm going to split this into 2n times x, instead of writing 2n plus 1. Because I can cancel out x to the 2n, then I have x cubed over x, which would leave me x squared in the numerator, and that x squared can actually come out front of this limit because, again, the x is not changing in this case. And I don't particularly need absolute value around x squared. Then it's the limit. N goes to infinity. 2n plus 1 over 2n plus 3. The function inside the limit is rational. The degrees are equal. Ratio of leading term coefficients are just 1. So this results in x squared. And this will converge whenever that's less than 1. Now, if we want to solve an inequality like x squared is less than 1, what I would do is bring everything to one side because it is a quadratic. Factor, so then x plus 1 times x minus 1, less than 0. And then just use a sign chart. So solving a polynomial inequality is generally easiest using a sign chart. So zeros are -1 and +1. If you test these values, if you put in like -2, it would be negative times negative, which is positive. If you put in 0, that would be a negative result. If you put in 2, that would be a positive result. So it looks like this would be less than 0 on this interval right here. So we have the interval currently from -1 to +1. But we need to know about the endpoints. So we'll do that next. We'll start with the endpoint x equals -1. Just plug that into the series and see where that takes us. So this would be -1 to the n plus 1. If I put -1 in for x here, it's going to be -1 to the 2n plus 1 all over 2n plus 1. All right, now there's going to be some simplification that can happen here. Let me go ahead and do that before I try and decide on its convergence here. All right, -1 to the n plus 1. I can actually write that as -1 to the n times -1. And same sort of thing for -1 to the 2n plus 1. It would be to the 2n times -1 to the first, okay? All over 2n plus 1. Okay, -1 times -1 would just cancel to a positive. And then I have -1 to the 2n, which is interesting because 2n ensures we have a positive value, right? So we're ensuring that we have a positive value, or I'm sorry, we have an even value, and if we raise a negative number to an even value, the result's always going to be positive. That's what I meant to say. So that term is always going to be just +1, which kind of disappears for us. So this results in the sum n equals 0 to infinity of -1 to the n over 2n plus 1. Now, we need to figure out if this thing converges or not. So I think maybe the easiest thing to use would be the alternating series test. So first thing we need is the limit as n goes to infinity of the non-alternating part of this to be 0, which indeed it is because the denominator is changing but the numerator is not. And then we would need this to be a decreasing sequence. So we would need this inequality to hold. So 1 over The n plus 1th term we've already determined earlier. It's 2n plus 3. That's got to be less than or equal to 1 over 2n plus 1. But cross multiply 2n plus 1 less than or equal to 2n plus 3. And if I subtract 2n from both sides, that's a very clear result because 1 is in fact less than 3. So this converges. And we have one other endpoint at positive 1. If I plug that into my series, it's going to be negative 1 to the n plus 1. And then when I plug in for x, it's going to be 1 to the 2n plus 1, all over 2n plus 1. Okay, so 1 to any power is just 1, so that's not going to have any effect on anything because 1 times anything is itself. And then effectively I have the exact same series. This would be the same thing as negative 1 to the n plus 1 over 2n plus 1 is what we just proved. So this also converges. By the alternating series test as well. But I'm not going to go through the details because we just proved it in the last endpoint. So that means the interval of convergence here is from negative 1 to positive 1, and both endpoints are included in this case.